Hello, and thank you for joining. In this episode of the optimization series, we will be talking about optimizing SQL Server on AWS. My name is Alex Zurenin. I am a senior solution architect at AWS. This presentation was prepared by my colleagues Rafet Dushik and Rekard van Rooyen and me. AWS Corporation, which you should be familiar with from the previous episodes, currently manages different SQL Server databases in their migrated environment. Many applications leverage SQL Server Enterprise Edition running in always-on availability group for high availability. This solution, while functional in their previous on-premises environment, is not the most cost-effective. So AWS is looking to reduce cost while still maintaining the same level of performance and high availability. AWS Corporation also interested in building a more robust disaster recovery capabilities that scale with their AWS workload. In this session, we will demonstrate how we optimize SQL Server cost by as much as 65% on AWS, while still maintaining the same level of high availability and similar performance. In the previous session, we optimized Windows Server at scale on AWS by eliminating traditional management software, improving the management of Windows Server running on EC2, and scheduling patch baseline for Windows servers. In this session, we will turn to optimizing SQL Server platform deployed by AWS Corporation on AWS. Specifically, we will look at what steps we can take to minimize run cost without sacrificing performance. To achieve this goal, we will attempt to separate compute and storage requirements, review recommended changes to AWS instance family used to host SQL Server deployment, consider benefits of using Amazon Managed File Server for Windows or Amazon FSx, and evaluate options for downgrading SQL Server from Enterprise to Standard Edition. Finally, we will look at optimizing backup solution for SQL Server databases. So, here is the architecture that was achieved after we optimized Windows Server at scale on AWS, which will be our starting point for optimizing SQL Server deployment. For this session, our area of interest would be subnets 5 and 6, which host SQL Server. Let's look at the SQL Server deployment in more details. The infrastructure deployed by AWS Corporation on AWS for SQL Server is based upon initial optimization and licensing assessment, which primarily focused on capacity and feature planning. Collecting performance statistics from the on-premises system, we identified the SQL workload requires about 30,000 IOPS to achieve required response time. To achieve this level of IOPS, OLA recommended deployment of SQL Server on R5 8x large instances. As for AWS VMs, maximum storage throughput depends on the instance size. At the same time, the CPU utilization stayed consistently low, indicating that the workload is I/O bound. For SQL Server on AWS, AWS Corporation opted for license-included deployment to avoid long-term licensing contracts with Microsoft and preserve licensing flexibility for potential future optimization and refactoring. Company policy requires maintaining 7-day worth of database backups. So to host backups, Current design allocated 16 terabyte storage on the file server. This architecture represents starting point for our optimization effort. For every optimization or re-architecting effort, it is critically important to establish performance baseline to be able to prove that the new solution does meet performance requirements. As AWS does not have native load that would closely mimic production, we decided to use industry standard HammerDB tool to establish baseline and measure proposed solutions. HammerDB has multiple setup and configuration options. To achieve statistically consistent results, we set each test duration to 10 minutes. We also selected option Use all warehouses to increase I/O load on the system, as we know that production workload is I/O bound. We enabled HammerDB autopilot feature to run series of multiple tests automatically. We selected several levels of workloads, which in HammerDB defined by the number of allocated virtual users. By increasing the load, we strive to achieve system saturation to identify maximum performance level achieved by the system. For consistency, we run each test multiple times. To avoid dependency between subsequent tests, we selected option to perform checkpoint after every test to save dirty pages. Results of our preliminary performance tests presented in this table. To perform analysis, we plot performance data against the number of virtual users. That's the level of load. As you may see from the chart, the first series of tests had much lower performance than the subsequent tests. We attribute this to the fact that during the first series of tests, SQL Server loads internal buffers. By the second series, it achieves steady state, so the results in the second and third series are very consistent. We plotted the results of the second and third series, as well as their average, at a larger vertical axis scale. The performance increase with the increase of workload level plateaued at the workload of 304 virtual users, as it saturated the system. So we use 304 virtual users as a baseline workload in subsequent tests. Based upon the results from preliminary performance tests, we configured HammerDB Autopilot to run 5 tests with the load level set to 304 users. The result of the first 2 tests are discarded, and then the results of subsequent 3 tests averaged to establish performance baseline. From our tests, current AWS Corporation SQL Server environment can provide performance level of 77,670 new orders per minute, which is the HammerDB universal performance metric. We will use this value to compare with the performance level achieved by other architectures. R5 8 extra large instance was selected to host SQL Server for AWS Corporation because of the requirement to provide sustained throughput of 30,000 IOPS to Elastic Block Storage, or EBS. So what if we separate compute and storage requirement by offloading storage to Amazon FSx? To achieve at least 30,000 IOPS from FSx, we configure it with 14 terabyte of storage and 1 terabyte per second throughput. By offloading I/O to Amazon FSx, we now have an option to scale down our compute node. We also change instance family to R5DN because the instances in this family provide enhanced networking throughput. This feature is important as in this scenario we swapped access to EBS for network access to Amazon FSx. This family of instances also provide locally attached, very fast NVMe storage, which we may use to store TempDB to improve performance and extend SQL Server buffer pool to compensate for lower amount of RAM on smaller instances. We carried out performance testing of the architecture based upon Amazon FSx using R5DN 4 extra large instances with 16 CPU. Then we repeated the same tests using R5DN 2 extra large instance with just 8 CPU. These smaller machines achieved level of performance within just a few percentage points of the original configuration based upon R5 8 extra large with 32 CPU. As the SQL Server license cost proportional to the number of CPUs, we see dramatic decrease of the run cost for the environment based upon Amazon FSx. It is interesting to point out that we see negligible performance difference between R5DN 4x large and 2x large instances, as the performance for the IO-bound workloads is primarily dependent on the storage subsystem, which was the same for both systems. Based upon these performance testing results, we can change SQL Server nodes configuration from original one with the cost of about $30,000 per month to optimized configuration with the cost of under $14,000 a month, resulting in about 54% of cost savings. Just look for a minute at these numbers. To achieve this result, we had to reach certain level of FSx performance. There are two factors that determine performance characteristics of your FSx file system: the amount of storage and throughput capacity that you configure for it. You may estimate these parameters using data from the documentation, but you do not have to be able to nail it right away. FSx allows you to change these parameters practically on the fly if you want to experiment or adjust performance. My colleague, Rafet Ducic, will demonstrate now how easy it is to configure FSx.
Hello, my name is Rafet Ducic, and thank you for joining me for this quick demo on creation of FSx for Windows. I'll be showing you how to create a file server, as well as how to set up initial configuration of it, and then modify it to increase the capacity as well as throughput. So let's go to FSx on AWS console, and from here we'll create the file system. And let's select FSx for Windows. I'm going to click Create File System and select FSx for Windows. File system name is optional. For deployment type, I can deploy this in a multi-AZ or a single AZ. Since we will be deploying SQL Server in multi-AZ configuration, I will choose multi-AZ. Please note that you cannot change the deployment type once the file system has been deployed. For the storage type, we have a choice between SSD or hard drive, and I'm going to leave it as default as SSD. For storage capacity, I will select 1 terabyte. After selecting 1 terabyte, a recommended storage capacity of 16 megabytes per second is provided, but I can choose my own throughput capacity. Here I'm going to choose 512 megabytes per second. For network and security, I can choose the VPC in which it will be deployed. So I'll select a quick start VPC, and the default security group has been selected. I'm planning to deploy SQL Server in private subnets 1A and 2A, so we'll select those. To provide for user authentication and access control for the file system, we have a choice between AWS Managed Active Directory or a self-managed Active Directory. We have already created afds.corp Managed Active Directory, so I will choose that. Next, on the review screen, we can verify all the details. And I'm going to click Create File System. After the file system creation has been completed, we can now select it and modify it. We can see that our file system is deployed, and here we can modify our capacity and throughput. For storage capacity, we can click on Update of the storage capacity and increase the storage capacity by either percentage or absolute values. I'm going to choose to increase this by 50% and click Update. After the update is going to be in progress. And after it completes, we'll be able to verify on the Update tab that it has been completed. In a similar way that we've been able to update our storage capacity, we can also update our throughput capacity.
Exciting results. But can we do even better than that? Achieving further savings would require replacing SQL Server Enterprise Edition with SQL Server Standard Edition. Can we do that? It depends on several factors related to whether customer actually takes advantage of specific features of Enterprise Edition. If the driver for deploying Enterprise Edition was primarily to achieve high availability using always-on availability group, then we can downgrade SQL Server to Standard Edition. However, SQL Server Standard Edition supports only basic availability group that is limited to a single database per group, which would work only for simple SQL Server scenarios. Thus, if we decide to downgrade edition of SQL Server, we will have to replace high availability implementation from always-on availability groups to SQL Server Failover Cluster Instance, or FCI. As in the previous case, where we focused on optimizing individual nodes, we're starting with establishing performance baseline. Implementing always-on availability group takes a toll on system performance due to the need for synchronous replication between nodes. Similarly, SQL Server FCI also takes a toll on performance as compared to a single node. Performance of both implementation for high availability, while slightly less than the performance of standalone nodes, is still within a few percentage points of each other. On the other hand, moving from Enterprise to Standard Edition reduces run cost by about another $3,000 per month. So, optimizing high availability cluster configuration allows us to further reduce cost from about $30,000 per month in original configuration to under $11,000 per month using SQL Server FCI with FSX for the total savings of about 65%. In the past, implementing SQL Server FCI in the cloud was rather complicated and required acquisition and deployment of third-party software. With the introduction of Amazon FSX multi-AZ deployment option with continuously available file share, creating SQL Server FCI on Amazon AWS became simple and easy. My colleague Rafet Ducic will demonstrate now the main steps of setting up SQL Server failover cluster instance using FSX for data layer.
From the console, I'm going to launch instances, and I will select Windows 2019 as the AMI for the instance. For the instance family, I will select the R5ND and select 2 extra large for the instance size. I'm going to put these instances in the same availability zone as the FSX is deployed, so 1A. And for Active Directory, we'll select the corresponding IMI role and join instance to the domain. These instances will need additional IPs for the clustering, so I'm going to assign 2 additional IPs per instance, one for the cluster and one for SQL Server. Let's increase the volume to 100 gigabytes as this will store installation media. I've already created a default group which allows communication within the VPC, and I'll hit the launch and select existing key pair. To launch the secondary instance, let's select the instance we just launched from the action menu, images and templates. I'll select launch more like this. On this screen, let's edit the instance details, and here we'll choose the second availability zone of 1B, corresponding to the FSX availability zone. After our instances have launched, let's collect the IP addresses of the instance, the primary IP as well as the secondary IP. These will be used in creation of the cluster. And for FSX file share, on the FSX tab from the actions, let's click on attach, which will give us the file share path. Here we have cluster details, the nodes, the primary addresses of the instances that will be used for clustering, the static IP addresses, and which will be used for cluster group. I will use the first of these instances that were created. Let's RDP into the instances that were launched, and we can see that they've joined to the domain. When the instances start, and we only see the C drive, but don't see NVMe available storage. That's because the drives have not been initialized. We'll start a PowerShell administrator. The first step is going to disable the firewall and initialize the disks. We will also schedule this disk initialization so that every time a computer restarts, these disks will be reinitialized. After the disk initialization, we'll grant the permissions to everyone to have access to the newly created NVMe temporary storage drives. For the cluster installation, we'll start installing Windows features, which will need to restart the machine. After the reboot has completed, I'm going to test the cluster, which is required for SQL Server startup, and then create a cluster. After the test has passed, we're going to create the cluster. The setup of the cluster has been completed, so let's go ahead and install SQL Server. I've already downloaded SQL Server Developer Edition. I'm going to start the installation and select Custom, as this will download the packages and install the SQL Server. While it's downloading, I'm going to install SQL Server Management Studio. The download instructions have completed, so let's go ahead and install the SQL and select SQL Failover Cluster installation. I will select SQL Server Developer Edition. And here we'll select Database Services. Our SQL virtual name will be SQL FCI01, and I will select the default instance. In the cluster network configuration, I'm going to enter the secondary IP for the first instance. For SQL Server configuration service accounts, I already created a SQL SA account, and I will enter it for both agent and the database engine. Additionally, I will select volume task privileges, otherwise known as instant file initialization. I will also add SQL Server administrator accounts that will have SA rights on the server. In the data directory, we will specify the continuously available file share residing on FSX. And I will add 8 files for TempDB, each of 80 megabytes in size. Here we are seeing the message that we need to verify the SQL Server account has the permission to the file share. So let's open the file share properties and securities tab and add SQL agent account with full control. Let's go back to an installation and click yes on the verification screen. And the install will complete. As the part of the SQL Server role creation, the cluster is going to create SQL Server virtual name for which it has create child object privileges in Active Directory. And here we are seeing that this is enabled to do so. To edit Active Directory properties, we need to add 2 features to local machine, the AD and the DNS server tools. From the local server manager, let's open Active Directory users and computers from the Tools menu. Here we see AWS Managed Active Directory. As this is the Managed Active Directory, we need to open AWS folder. And let's go ahead and copy the name of the cluster. When we open the properties, we don't see the security tab, which is available only from advanced features view. So from the view, let's select advanced features. And now let's expand AWS and right-click computers and select properties. Now we see the security tab, so let's add the cluster name. And since this is a computer object, let's select this as an object type. In the permissions view, for this object, let's select create and delete all child objects and click OK. Let's go back to our setup and retry. And now the setup completes. The secondary node, we will install SQL Server and launch the install. Here we'll select the secondary IP address for the second server. And I will re-enter the SQL SA passwords. After this, the installation completes. Now we'll move the TempDB files to the NVMe drive and set up buffer pool extensions. So let's open SQL Management Studio and connect to the SQL Server virtual name. Here I have a script that will replace the drive letter on the path for the TempDB to the Z drive. This will print the command to move the TempDB to the Z drive. After executing, we'll need to restart the SQL Server. This option is not available from the Management Studio, but instead this will be done from Cluster Manager or Server Configuration Manager. So let's go ahead and start and stop the role, which will restart the SQL Server and then move the TempDB files. To take advantage of the NVMe storage, we can place the buffer pool extension on the NVMe storage as well.
SQL Server Backup Solution deployed by AWS Corporation closely mimic their on-premises approach. It has several inherent shortcomings, including management and configuration overhead and limited storage capacity for database backups. Instead, we recommend solution based upon Amazon Storage Gateway. We configure Storage Gateway on i3-EN extra large instance, which offer 2.5 terabyte of ultra-fast NVMe storage. Using NVMe storage as cache for backup files will reduce SQL Server backup time. Cached backup files are uploaded asynchronously to Amazon S3 infrequent access storage, which offers 11 nines of durability. This durability level significantly exceeds durability of files stored on a file server. Due to the low cost of S3 infrequent access, we can increase backup retention from 7 to 30 days. Besides multiple operational benefits, this backup solution is also almost 40% cheaper than the original one. This is how the AWS Corporation AWS architecture looks after we performed optimization of SQL Server deployment and respective backup solution. Let's summarize the steps and results we achieved. In our approach to optimizing SQL Server on AWS, we replaced traditional way to deploy SQL Server using elastic block storage with the innovative approach based upon offloading storage operation to Amazon FSx. Using this approach, we first focused on optimizing individual nodes. Then we investigated option to optimize the whole cluster, replacing SQL Server Enterprise Edition Always On Availability Group with SQL Server Standard Edition Failover Cluster Instance as the high availability solution. Each of the proposed solutions was extensively tested to assure the customer that implementing recommended solution would maintain expected level of performance. Then we reviewed original backup solution and offered modernization based upon using native AWS services, which besides lower cost offered better functionality, scalability, and durability. Implementing our recommendations will reduce run cost of SQL Server and related backup solution from about $32,000 per month to under $12,000 per month for significant overall savings of about 63%. I hope you are as excited with these results as we are and will find ways to use this approach in your design and deployment of workloads on AWS. If you like this presentation, please review other videos in the optimization series. Thank you for your time and staying with us through this presentation.